Welcome again. This lesson is going to be on ethers. We have done several functional groups now, alcohol being the most recent one. We move now to ethers, and this is the general form of an ether. So what we have here is the R again, representing a hydrogen or a continuation of, well, in this case, it would actually have to be not a hydrogen, it would have to be a continuation of an alkyl group on either end, separated by an oxygen. Okay, now just reviewing our priority groups again and paying attention to where ethers are compared to the other groups we have done. So alcohols or aldehydes, ketones, and alcohols are groups that we just did, and usually what we saw was after one functional group we did another one that was usually of higher priority. In this case, we're going back down the list and we are here at ethers. Now some priority lists might be slightly different than others. We're going to stick with the one provided in this course, and ethers goes before alcohols. Okay, we haven't done amines quite yet. That will be coming up very soon, but notice that ethers go below alcohol. So if you see an alcohol functional group, an OH group, then we know then that this will take priority in terms of naming and numbering of locants. Okay, so not too many rules here, except that there are two ways of naming ethers. And the key is to always choose the easiest one. And you'll see as we do examples that one method is probably easier than the other. I'm not going to read this with you, I'm going to jump right into the example so we can put these rules into context. But the next slide, I think, summarizes these rules a bit better than those than that previous one does. So one rule essentially is just use the branch method of naming. I call it the branch method of naming. And that is on either side of that oxygen, name them as branches. It's all I'll say for now because it'll make more sense again if we look at examples instead of trying to dissect what this means. Okay, so that was a branch method. The other method, what I call the parent method, is similar to what you've done in the past. So choose a parent as you would normally. So that part hasn't changed. Now what does change is writing the new portion of the ether, so the oxygen together bound to an alkyl group. So for example, if your alkyl group that is bound to an oxygen is, let's say, methyl, the name will change because you will remove the YL and you will add oxy to it. So the ether component of that compound would then be called methoxy. Okay, again, that's all I want to say about this for now because we're going to dissect that by doing examples. So here are first two examples. Okay, so we're going to name this one in both methods. So let's try using the parent method first. We're analyzing both methods. Okay, so in this method, I'll pull out a highlighter instead. That might work better. Okay, so as the parent, you're going to choose the side that has the longest chain. So that's very similar to what we've done many times now. So this side has 3 carbons. Make that larger. This side has 3 carbons, 1, 2, 3. So that's going to be the parent, and it's a fully saturated hydrocarbon, so it's going to be an alkane, which means you're going to say propane. And off of the second carbon, we have a methyl group. Now we change that YL, add oxy, and that becomes the branch. Hoping I don't reveal the wrong answer. Here we go. Well, not the wrong answer, the other version of naming, and I didn't, so that's good. So off the second carbon, we have a methoxy off of a parent called propane. So that's the parent method, or also called the oxy method. Again, those are just terms that I've made up and how I remember the two methods of naming ethers. Okay, the other method, so I'll erase this. Well, no, that actually can stay. I will switch back to the highlighter. Let's choose green. Okay, the other method is treating either side of that oxygen in this ether, treating either side as if it were a branch, an alkyl branch. So on this end, we have a methyl, and on this end, we have 1, 2, 3 carbons. It's not propyl, right? Remember, this is going to be isopropyl because it's attached to the second carbon. So this branch would then be isopropyl, and this would be methyl. And all we do in that case is we add the suffix ether. So watch what happens. And again, you name it alphabetically, or you list their branches, these two, alphabetically, followed by the word ether, and this is the name. Right, alphabetically, isopropyl, methyl, ether. Isopropyl is this branch, methyl is the highlighted green. Attach the word ether to it, and that is your name. So 2 methods of naming. This again, the first method is the parent method, or the oxy method, I like to call it, or The second method here is a branch-branch method. Okay, another example. So here we have a possible parent on this side, possible parent being 2 carbons long. So that can be ethane, and off of ethane, off the carbon here, so we can say that that's carbon 1. Off the first carbon, we have a methoxy. So methoxy, ethane is one possibility. Another one could be that we name both sides by their branch. Here is ethyl, here is methyl. We attach the word ether to the end, listing those branches alphabetically, and we get these two methods, or these two possible names. So methoxy, ethane. Now you could have written 1-methoxyethane, but because it's off the first carbon, that's implied. Either way is correct. The other method, you list alphabetically your alkyl groups first, so ethyl first, methyl, followed by the word ether. Now when it comes to spacing here, I've seen this spaced out with a space between each of these, so space after methyl, space after ethyl, space after methyl. I haven't seen a lot of consistency here, nor any rules written, so don't worry about spacing. I'm not going to be that picky. Okay, moving on. All right, so we get a little bit more complicated here. This is a parent benzene ring, and off of benzene, off of, let's say, the first carbon, because that would be the easiest or the lowest number to give it, we have a methoxy. So benzene is the parent, methoxy is the branch. So this is the parent method of naming, or the oxy method of naming. We have methoxybenzene. Now the other method of naming is treating both sides as if they were branches. So if we do that, this side here, when benzene is a branch, try to remember what that branch name is. Okay, while I highlight this, and this is of course methyl. So what is benzene as a branch? Hoping you're thinking about phenyl, right? So list these branches alphabetically, followed by the word ether, and that is the other possible name. So methyl, phenyl, ether. And look here, they have spaces, but either way is fine, at least for our course. Okay, so methyl, phenyl, ether, that is the name. These are the two possible names of this compound. All right, next example. Okay, so here is one possibility. We have, actually, I think I've already revealed it, yes. Okay, so this is a good example, actually, of something that it's probably easier to name using the parent or using the oxy portion. So here we have a parent benzene. Okay, so this parent is benzene, and off of benzene we have a couple things going on. We have bromo, right? A halogen right there, and here we have methoxy. So the best way to name this, the easiest way to name this, is using the parent method, because imagine trying to name this end, as if it were a branch. First off, it would be a complex branch, and we always try to avoid those. This end would be easy, right? That would be okay because it's just methyl, but this would give you quite a complex name. So the best way to name this is using the parent method of naming, and that would have you name benzene as the parent. Off our fourth carbon, because alkyl halides are really low on the priority list and ethers trump that. That means this has to be carbon 1, this is carbon 2, this is carbon 3, and this would be carbon 4. So locant 4 for bromo, locant 1 for the methoxy. Again, you don't have to write the 1, but it is implied if you do not. Correct if you do, correct if you don't. So 4 bromo 1 methoxybenzene is the correct name. Okay. Common mistake name written here. Okay, next. So this is now an example where the ether does not play the higher priority role, right? So we are not going to number, in this case, carbon 1 here. We begin, well, I guess, yeah, actually, we could. See, I'm thinking as we go along. Okay, so numbering can begin here, carbon 1, carbon 2, carbon 3, because either way, the higher priority group is going to get that number 2, even if we try to numbering here. And we're going to prefer this method because that gives us the oxy portion, the methoxy portion, a lower number being number 1. So here, the parent is going to be a propane, but the propane is defined not by the ether, it's defined by the alcohol. So 1, 2, 3, propanone, right? 2, because it's attached to the second carbon. Off the first carbon, we have a methoxy portion. Okay, moving on. We'll continue with several more examples. Here we have, okay, I think we're going to try name this in two different ways. So here we have a possible branch highlighted here in yellow, 1, 2, 3 carbons. That's propane, off of propane. We have a methoxy and we have a methyl group, right? Put those together. We have methoxy off the second carbon. Also off the second carbon, we have methyl, so 2-methoxy, 2-methyl off of the parent propane. But we can name this, we can name this portion here. We can name this as a branch, and we can name this as a branch, right? This one's easy, methyl, and hoping you remember what this group is. Perhaps it's been a few days since we've seen this, or a little while since we've seen that, but this is tert-butyl. So another possible name is tert-butyl methyl ether. Tert-butyl methyl ether. Now you might be wondering, but wait, T comes after it comes after M. Why is it not methyl tert-butyl ether? Okay, I know I didn't make up the grammar in IUPAC, but just like you don't use the Greek prefixes di, tri, tetra, penta, and so on when you're considering alphabetizing, you also ignore tert and sec because all they do is they think of them as prefixes that describe how the butyl is geometrically arranged. I know, does make a lot of sense. Like I said, lots of exceptions. So it'll be tert-butyl because we're naming off of the B, followed by the M. Okay. Next, here we have your ether portion. Okay. This ether portion is not methoxy as we've commonly seen in the last several examples. Here we're going to have ethoxy, and we have a carbon chain where we're going to start numbering. Now there are two possibilities. You can say carbon 1 is going to be on the left-hand side, carbon 1, 2, 3, 4, 5, 6. Okay, but if we remember our priority groups, ethers are higher priority than alkenes. So this would be the wrong way to number. Instead, we should number 1, 2, 3, 4, 5, 6, giving our ether the higher priority and numbering starting on the right-hand side. So 4-ethoxy-2-methyl, 1-hexene, or just hexene, is not the correct way to name this because it doesn't prioritize the ether. So 3-ethoxy, 5-methyl, 5-hexene. Yes, these are greater numbers. I can see why perhaps it might be very tempting to name it this way, but if we follow our priority list, we're going to name it this way. Next. Here we have another alcohol, so this alcohol is going to take priority. We have an oxy component branch here, your ether branch here, and notice this looks like isopropyl, so we're going to see isopropoxy as a branch. Off of a 1, our numbering system has to begin here because we're prioritizing the alcohol, so 1, 2, 3, 4, so it's going to be off of a butane, which changes to butanol because of that priority alcohol. Off the third carbon, we have isopropoxy. So put that together with the ether branch. We have 3 isopropoxy, 1 butanol. Again, the 1 is optional. You can have it or not, and you're fine. Okay, now instead of naming, we're going to draw. We're going to show you drawings of, or diagrams, pictures of what the name refers to. And this is a good time to pause the video and try these yourself. Okay, so hopefully you've paused it and you've given it a good try. Remember, if it is wrong, don't erase it. Correct it instead. So 2-ethoxybutane. Here, this is the parent method of naming, so I would suggest draw the butane first, and then off of the second carbon, attach an ethoxy. So attach an oxygen with an ethyl group, and you get this molecule. Right, so 1, 2, 3, 4. 4 carbons long. Off of the second carbon, we have oxygen with an ethyl group attached to it, and that's the structure. The next example is using the branch-branch method of naming, that is ethylpropyl ether. So oxygen in the center, draw an ethyl, 2 carbon, draw a propyl, 3 carbon on the other side, and your structure looks like this. Okay, again, make corrections if you need. Don't erase your mistakes. That's it for nomenclature. Now, how ethers are formed. not too complicated of a process. Essentially, you need two alcohols, right? They can be the same, of course, they can be different. And your catalyst here is sulfuric acid, similar to other reactions we've seen. So sulfuric acid, sometimes this is called a dehydration reaction because as you can see, water is being removed, so it's being dehydrated. Think of this as OH, H becoming water, right? HOH, and this creates an ether between the two alkyl groups. Okay, so a couple of examples. So here propanol, right here, propanol reacts with butanol in the presence of sulfuric acid. So you can write just H plus is just fine, or if you want to write H2SO4 aqueous, that's perfect too. So that combines, and we see that OH and the H combine to create water. That is removed, and what we have here is butyl propyl ether or propoxybutane as the product. Okay, you've practiced this enough now. Take a few seconds and try this yourself. So pause the video, write the product and any byproducts you have in this reaction. All right, so hopefully you've paused it. This is ethanol plus itself. So ethanol reacts with itself in the presence of sulfuric acid. Here's your catalyst, and all we get is dehydration reaction. Byproduct is water. And look, we have what you would call diethyl ether. Now, if you say ethyl ether, kind of redundant. Remember, we're using wherever we have multiples of anything, you use your Greek prefixes. In this case, di, because there's two, so diethyl ether is the name of that product. Don't forget your byproduct, water. Okay, now properties of ethers. If we compare the boiling point to that of the parent hydrocarbon, we see that it is going to be, boiling point is going to be higher because of that dipole end of the highly polar oxygen molecule that is now present. But if we compare it to alcohol, alcohols are going to be higher in boiling point because they have an OH, which allows for greater intermolecular forces, namely hydrogen bonding. Now, because ethers have both a polar and a nonpolar component to their structure, they can be miscible in both polar and nonpolar solvents. Of course, if you increase the length of any alkyl end, you increase the nonpolarity of the molecule, decrease the miscibility, anything that is polar. And because of its miscibility in both polar and nonpolar substances, ethers are toxic to humans, or toxic to life, because they can accumulate inside. They can accumulate inside lipids. Okay. They, of course, are then not easily extracted by your kidneys. Okay, so reactions of ethers, generally unreactive. We'll talk more about reduction oxidation reactions later on. But generally, if an ether is reacted with a hydrogen halide in the presence of heat, you'll get an alkyl halide and an alcohol. Now, this mechanism and reaction does get a bit more complicated than I'm going to show you, so I'm simplifying it for the purposes of this course. So what we have here is we have an ether. So again, this is diethyl ether, like the example we just saw. Diethyl ether in the presence of a hydrogen halide, in this case hydrogen iodide, and heat, acid and heat. Make note of that. Need an acid. Don't think I wrote that down, but you need an acid. So acid and heat, I'll correct that here, plus H plus ions. That's not a G, that is a Q. Okay. So that's going to cleave. It's going to cleave this ether, and one end is going to get the alkyl group, right? One end is going to get the alkyl group, and the other one is going to get, from the presence of water in this acid, is going to become your alcohol. Okay, now this can be further reacted. Now this reaction can be controlled by limiting the hydrogen halide used. A substitution reaction can occur here, right, where you can have iodine, in this case, replacing your OH group with a byproduct of water, right? So OH, H, H2O, iodine replaces that, and we have another alkyl halide. Of course, this can be limited by limiting your hydrogen halide. Back to grade 11, limiting reagents. Okay, another example. Here we have ethyl phenyl ether. cleavage, otherwise known as anisole. Cleavage of this can occur. Now here it says we're limiting, this is our limiting reagent. We're limiting hydrogen iodide in the presence of acid and heat. We get an alcohol, benzenol or phenol, together with iodoethane. Now, which one gets the OH and which one gets your halogen? For the purposes of this course, we're going to say either, but that is not entirely true. It depends on the carbon and its surrounding atoms, but that is beyond the scope of this course. So either one is fine. I could have attached the OH here to this ethyl or to this ethane, and the iodine to the benzene. Both are acceptable for this course. Good. A quick fact: you've probably seen maybe in some old movies that someone's covered in the face with some rag or some cloth with ether, soaked with ether, and they pass out. It used to be used as an anesthetic, especially in dentistry, until it was discovered later that it doesn't actually suppress pain; it just knocks you out. So it must be a terrible moment to endure when you're passed out, yet you can still feel pain. Very strange. Not so nice, I imagine. And that is your home fun. There's an alcohol and ethers worksheet posted online. Post any questions you have. I hope this helped.